Okay. Okay, so welcome again to yet another lecture in our C-star algebra and groupoids course. Today we will finally get to groupoids, so that's kind of exciting. And yeah, this is actually lecture number 11. I think I might have said that last lecture was lecture number 9, but it was pointed out to me that no, that was lecture number 10. So that makes today lecture number 11. That's the minor thing there. Okay, so today I really wanted to get into one of the main topics of this course, which is Étale Groupoids. So first though, let's just do a quick review of what we're talking about last week. So remember we were talking about C-star algebras defined from finite groups. So given any finite group, we found out we had this nice C-star algebra, which we denoted by C star of G. And at first we defined this by representing the elements of G as operators on a Hilbert space defined by G. And then we showed that actually in the end you can do some identifications and actually identify this C-star algebra G again with certain functions, with basically all functions on G to the complex numbers. The product, which corresponds to the operator composition when we defined it originally, turns out to be this thing known as convolution, right? So the convolution of any two functions, A and B on G, is simply the sum of all the products of this form, AF times BG, where you take the sum over all those Fs and Gs such that the product is equal to H, right? This thing on the left here. So that gives the product. The star operation, on the other hand, because it's a C-star algebra, we need a star operation, was given just by this kind of, we might call it conjugate transpose. So A star is another function on G, except now the value of A star on G is determined by the value of the original function A at G inverse, not at G. And it's not just this value, you also take the conjugate, the complex conjugate, right? To be able to give you a nice antilinear function, which gives you your star operation. As for the sum and scalar products, well, that's easy. You just do those pointwise, right? So sum of two functions on G, you just sum up the functions at every single point. So all these operators give you a nice star algebra, and the extra sort of analytic structure here to make it a C-star algebra comes from this norm. So the norm here is what I think I might have called the B norm, which itself is defined from a 2 norm. So I guess the real order really here is that you first define a 2 norm on these complex valued functions on G by using convolution. I mean, this is not how we defined it originally, but this turns out to be equivalent. So the 2 norm of sum A is what you get by looking at the convolution of A star A and looking at it just at the value E, the unit of your group. So you look at that value and take the square root, and that will be A star A of E, A star A of E is always going to be positive. So the square root is always going to be another positive number. It really is a well-defined norm. And indeed, by looking at the value of any function just at E, this gives you a nice trace. So that's why we're denoting it by tau here as well. So that gives you your 2 norm, and you're giving this B norm A here is really just the operator norm of A when you view it as an operator on your Hilbert space. Right, when the operation here is just left multiplication, right? B goes to A times B. So as usual, when you're looking at operator norms, the operator norm is defined as the supremum of the norm of all the values of AB, where B is taken to be, where you take the supremum over all B in the unit ball. All those B's with 2 norm, at most 1. That gives you the operator norm, which in this case is the B norm and is exactly the norm we need to define the C-star algebra structure, right? So the C-star algebras are in particular Banach algebras, but also they have to satisfy the C-star norm equality. Okay, and as I just mentioned, this tau here is the canonical trace on your group C-star algebra, C-star G, right? Just by taking the value of A just to be the evaluation of A at the identity element of your group. And it's canonical, by saying this, I'm not saying it's unique in any way. There are many other traces you can usually define on a group C-star algebra, but this is sort of the standard one, which is useful for many things. For example, like defining the 2 norm. Okay, and we had a look at these groups. We did some preliminary investigations, some very basic representation theory of finite groups. And we found in particular that these finite groups all yield finite dimensional C-star algebras, and quite an interesting array of these finite dimensional C-star algebras. But they don't yield all those finite dimensional C-star algebras. The standout example being Mn. If you just look at n by n matrices for some n greater than or equal to 2, this will never be the C-star algebra of some finite group. And the reason is very simple, and that is that we showed C star G always has some one-dimensional ideal. Okay, and so in particular, when you're writing, did I write this here? Like, I didn't write this here, but so when you're writing your group C star algebra in this sort of normal form that Wedderburn looked at in the early 20th century, there's always going to be one summand which is just C, complex numbers. Whereas in Mn, on the other hand, well, this just does not have such a one-dimensional ideal. Mn is a simple C-star algebra, so it's never going to be of this form. So that immediately gives you some kind of motivation for why you might want to consider something a bit more general than a group, namely a groupoid. Maybe this might actually give us exactly the sort of tool we need to be able to define all finite dimensional C-star algebras in a nice, combinatorial or algebraic way. And this is exactly what I'm going to talk to you about today. Okay, so let's first, just to start off, talk about a very general kind of structure, which I'm going to call a semi-groupoid. So a semi-groupoid is simply a set together with some partially defined product, right? Okay, but it does have to satisfy one extra thing. We want our partially defined product to be associative. Okay, so this is associativity in the usual sense, right? If you have a triple product, ABC, it doesn't matter if you take the product of AB first and then multiply by C, or the product of BC first and then multiply by A on the left. You do have to be just a tiny bit careful here, because we're only assuming it's a partial product. We're not assuming it's defined on every pair of elements, in S. We have this distinguished set, which I'm denoting by S2 here, which tells you exactly the pairs for which the product is actually defined. So this equation here, the way you interpret it in this context is you say that the left-hand side is defined precisely when the right-hand side is defined, and moreover, both sides are equal in that case when they're defined. So I sort of wrote that out here in terms of S2. So in particular, the pair AB is in S2, and the result of multiplying AB and the element C here, that pair is also in S2. Well, that's telling you precisely that the left-hand side is defined. And likewise, this is telling you that the right-hand side is defined. So the left is defined differently, the right is defined, but then of course they still have to be equal in that case. So that's what I'm going to call a semi-groupoid. There are some people call these, I think, partial semi-groups, and people also call them semi-categories, although semi-categories usually are slightly more restricted. But yeah, in this course, we'll just call them semi-groupoids. We'll move on quickly to groupoids, and then we won't really need to talk about these much more. But this is a convenient context in which to define some basic concepts, like a unit, for example. So a unit in a semi-groupoid is simply any element which basically does nothing whenever the product is defined. So if the product AU is defined and U is a unit, then what this is saying is that it just gives you back A. So basically, U, sometimes people say U is a neutral element with respect to the product. So it really does nothing, at least when it's defined, right? So I mean, this is a sort of feature of the fact that you have a partial product means that you can actually have many different units, where the units themselves you can't multiply them together. So in this case here, if you can multiply an element A on the right by some unit element U, then we call U a source unit today. And likewise, if you can multiply U on the left of some B, right, then you will call this U here a range unit of B. And this, well, this terminology kind of makes sense because it's not too hard to show that source and range units, when they exist, are in fact unique, right? You can never have two different source units for the same element A or B, right? So the proof is pretty simple. Take two source units, let's say, TU of some element A in our semi-groupoid S. Okay, well, by definition, we can write A as AU, right? It's a source unit. But then A is also, the T is also a source unit for A. So I can also replace A in this expression here by AT, and then again, multiply on the right by U. But associativity, we know this is defined. So associativity is telling us that the other way of multiplying this triple here is also defined and gives us exactly the same value. In particular, T and U can be multiplied together. And then the fact that both T and U are units and that this product is well defined means that it has to be equal to both T and U, right? Both of them are neutral. So U multiplying by T should leave it unchanged. On the other hand, T multiplied by U should leave it unchanged as well. Okay, so they're the same. Very elementary, but I think worthwhile thing to note. And now that means we can introduce some notation, which we will use throughout the rest of the talk. And that is that for any element of our semi-groupoid, we denote the source and range units, if they exist, by these elements here, SA and RA. So you can view S and A here, the source and range, as functions or partial functions at this point, right? They may not be defined everywhere on S, but when they are defined, they are unique. And maybe let's make some more sort of observations about these units. So let's say that X is a source unit for some A, doesn't really matter what. Well, then actually it turns out it's automatically a range unit for some A as well. And in fact, it's a range unit of itself, right? And it's a source unit of itself as well, right? Because if you just, again, do some simple rewriting, let's say A is equal to AX because X is a source unit of A. But then again, we can replace A once more with AX. And we have this triple product. And you can see I'm removing the brackets now because things are associative. So we no longer really have to worry about whether we're taking the product of AX first and then the product with X on the right, or the other way around. Okay, so what this tells us is that because this triple product is well defined, in particular, X can be multiplied by itself, that is well defined. And then the fact that X is a unit tells you that, okay, the only possibility for the result of X times X is X itself. And by definition, this tells you that, well, X is an idempotent, definitely, but moreover, it is the source unit of itself, and it is the range unit of itself. Okay. So, and this applies to pretty much all units, right? Like the only time this would not apply to a unit is if the unit could not be multiplied by anything at all, if it was sort of a trivial unit in some sense, and we won't worry too much about them, they will disappear quite quickly. But let's denote for the moment all units by just S to the 0, right? So, so what this previous result is really saying is that if you look at the image of this map S, it's actually the same as the image of this range map R. And put another way, this is just the collection of all elements, all units which are idempotent, which you can at least multiply by themselves. Right? Another few simple observations is that if the range unit of some A exists, well then, and the product of A and B is well defined, well then that product AB also has a range unit, and it has to be exactly the same thing. Right? Because, well, again, applying associativity, if AB is defined, we can replace A with the range unit of A times A, and then we can take the product the other way, right? Put the brackets around the AB. So this is really just the range of A times AB. So, okay, it's well defined. That has to be the range unit of AB. And exactly the same thing applies to source units. It's just, now it's the element on the right that is important here. So the source of AB has to be the same as the source of B. Okay, and in a similar manner, you can show that when, let's see, when SA or B, yeah, I mean, this is, yeah, so we're still looking at this product AB. We're assuming still on this line, which I should have probably made explicit, but AB is defined. And if AB is defined, and either the source of A or the range of B is well defined, then in fact they have to be, then the other is well defined and it's equal to the other one, right? Simple argument, look at AB, replace it with, let's say, a source of A, assuming that's defined, move the brackets over by associativity, and this is saying that SA can be multiplied by B, i.e. it is a range unit of B. Yeah. And it seems like a almost trivial observation, but it's really the key, because it's the converse of that uniquely that defines what a category is. So a category in this context is simply a semi-groupoid where this reverse thing also holds, that whenever well, for one thing, source and range units always exist in a category, and that moreover, if you have two elements A and B, and the source of A is the range of B, then this should imply that the product of A and B is indeed well defined. And this may not be, I mean, I'm guessing you've probably all seen, the notion of a category before, and this may not look immediately like this is what I'm talking about, but it really is. The usual definition of a category, you recall, is you have this operation and it satisfies a slightly more complicated notion of associativity, and you have these objects floating around, and the objects determine when you're allowed to multiply to morphisms. And this is exactly what we have here. It's just our semi-groupoid S just consists of all the morphisms sort of jumbled together. And if you want to extract objects out of this thing, well, you just basically take your units doubling as objects, right? Or conversely, if you have a category, then basically throw away the objects and just view all the morphisms as a single set with a partial product. Pardon me, and you'll find that all these axioms really here are satisfied. So that these are just two different ways of looking at the same thing. In this area, it's generally more convenient to look at things like categories and groupoids, which I'm about to introduce, in a more object-free way. This just makes your life a bit easier. Okay. So what next? So inverses. So we're still in this realm of semi-groupoids, right? So we have a semi-groupoid, and A is just some random element of your semi-group. And we say some other element, which is usually denoted by this A to the -1 here. We say it's an inverse, as you would expect, if both A inverse, and inverse A are units. Right? Okay. And well, firstly, note this is indeed a symmetric relation, right? If A inverse is an inverse of A, well, then A itself is an inverse of A inverse, right? Another thing to note is that, well, let's say we have a unit, right? And well, let's look at the inverse of that unit, assuming it exists. Well, then a simple calculation tells you that, well, okay, if U inverse is defined and U is supposed to be a unit, well, that should do nothing to U inverse, right? That should just give us U inverse. But at the same time, once I know that, I can replace this U inverse here with another U inverse, right? But that tells us that this, well, it tells us that U is defined as a product, but it also tells us that this has to be equal to U, because remember, by definition, to be an inverse, this means this U inverse is a unit. Right? It should do nothing to U. Okay, so in summary, what this is really saying is the only possible inverse of a unit is that unit itself, right? So inverses are unique, at least when we restrict to units. They will be unique in a more general context, we will see very shortly. But just a little bit of notation here. Let's denote the inverses of, or the invertible elements in your semi-group, just by this S times, this little multiplication symbol. So what this, another way of saying this, if you like, this little observation above, is that if you look at all units which are also invertible, well, that's really just the collection of all elements such that U is equal to U times itself. Okay. Which is exactly what we had before. Remember that these units here are also the units which are the source units of something, or the range units of something. And, so there's just different ways of excluding these, I guess, trivial units where you can't multiply them by anything. Okay, now let's say we have an inverse. So A has an inverse denoted like so, and let's assume, moreover, that this A inverse is not a sort of degenerate unit, that it is indeed of this form here. You can indeed multiply it by itself. right? Okay, so writing that in full, what that means is that AA inverse is the same as AA inverse, right? But then you look at this product here and you say, well, that actually means that in particular, these triples here, AA inverse A, and moreover, A inverse A inverse, these are defined, right? Okay, and you can also see that they're defined, and you can also easily work out what they are, right? Because A inverse A, well, by definition, this right-hand side has to be a unit. So that's really just A. Or equivalent, you could look at the left-hand side and say, well, that's a unit. So it has to be A. Right? Okay, so in particular, this A inverse A here, if you look at this expression here, this appears to the right of A. So this has to be, in fact, a source unit of A. Or equivalently, looking over here, you see that this A inverse A appears on the left of A inverse. So it's also the same as the range unit of A inverse. Okay. And likewise with, the range of A is A inverse, which is exactly the same as the source of A inverse. Okay, so now we come to the all-important notion of a groupoid. So a groupoid is simply a semi-groupoid, right? You have an associative partial operation on your set, such that, moreover, every element is invertible. Okay. So some people like, if you're looking in category theoretic terms, it's basically it's a category where all morphisms are isomorphisms. Right? Or some people would say maybe a group with many units in a more imprecise way. So let's talk more about groupoids. Well, the first thing to note is that a groupoid G is indeed a category. And in this category, inverses are unique. And moreover, you have a couple of elementary relations you would expect, right, from group theory. That the inverse of an inverse is itself, and moreover, the inverse here reverses the order of multiplication. It turns a GH into an H inverse G inverse. Okay, well, first note that we were looking on the previous page, right? Remember that if G inverse G is, well, it has to be a unit, but if it's also invertible, and we're assuming everything is invertible here, well, then it's one of these non-trivial units. And so in fact, it has to be the source unit of G itself. And likewise, GG inverse, that has to be the range unit of G itself. So in particular, all elements, if you're assuming all elements have inverses, then it immediately follows that all elements also have sources and ranges, which is part of the definition of a category in our sense. Right? So all elements have source and range units. In particular, all these units are also invertible, right? Okay, so and now we want to show inverses are unique. Well, okay, take another inverse of G. Let's call it G prime. Okay, well, we know that G inverse is equal to G inverse source of G inverse by the definition of a source. Okay, but that's, as we did this calculation on the previous page, we remembered that the source of G inverse is always equal to the range of G itself. Okay, but then the range of G, it's equal to, the range of G is again equal to like GG inverse, right? But we're assuming that G prime is also an inverse. So it doesn't matter if we write GG prime instead of GG inverse here. This is still should be the range of G. Okay, but then you notice that, okay, G inverse G, it's meant to be a unit. So you multiply by G inverse, this should just leave it unchanged. It should be G inverse. Okay, so going back to the beginning, we've worked out that G inverse is actually the same as G prime. Inverses are indeed unique. The fact that G inverse is just G, well, that's really that observation I mentioned at the very beginning, that being an inverse is a symmetric relation. The G itself is an inverse of G inverse, right? And this inverse now is a true function. We don't have any freedom in choosing different inverses. So we know that this function has to satisfy this condition right here. And finally, we want to show it's a category, right? And remember that was that extra key condition that if the source of some G is equal to the range of some H, then we should be able to multiply them together. So let's assume this is true. Now let's look at source of G. Well, source of G is the same as source of G, right? However, we're assuming that this is the same as range of H, so we can rewrite it like so. But then we can also rewrite it in terms of inverses to get this product of four things right here. but in particular, you have this GH in the middle here, right? So by the associativity, this tells us that indeed GH is a valid product. And so G is indeed a category. And the last but not least, we just want to show this condition up here, that the inverse reverses the product. So let's look at yeah, so the source of H inverse G is equal to the range of GH. Okay, well, why is that true? Okay, because okay, easy, yeah, because well, the source of H inverse G inverse, that's equal to just the source of G inverse, which remember is equal to the range of G, which is equal to the range of GH, right? When you're looking at sources and ranges, really only one of the elements is relevant here, right? If it's the range, it's the left element. If it's the source, then it's the right element. Okay, so these two things are definitely the same. Okay, so particularly you can, because we know it's a category now, we know we can multiply these two pairs together. So you get this quadruple here now. Okay, but then you say, well, G inverse G, that's just a unit. That shouldn't affect anything. I can just delete it from the middle. That leaves me with H inverse H. Again, another unit. So I should be able to just basically, yeah, I guess I can't delete it, but this is indeed a unit. So this tells you that indeed H inverse G inverse GH is a unit, and the same, pretty much the same kind of argument shows you the same thing for the product the other way around. So indeed, the unique inverse of GH has to in fact be H inverse G. And so this is exactly what you would expect from groups. We're just dealing with this slightly more general context where we have a partial product. And one thing to note, which maybe will be more important next lecture, I guess, but this star operation, the star equation, I guess here, these two properties here, in a certain terminology, what they're really saying is that G is a star semi-groupoid. So where the star in this case is just the inverse. There are more general star semi-groupoids, which will be important later on. So star semi-groupoid being your groupoid with this involution, like such that GG star is equal to G, and the star reverses the order of multiplication. Okay. So that's groupoids. We know the definition, so it's time for a few simple examples. Well, of course, groups are groupoids, right? There's nothing preventing the product from being defined everywhere. Maybe not the most interesting groupoids, but they are perfectly valid groupoids. And indeed, if you have a groupoid G, there's various different ways of saying that G is a group. This is really equivalent to saying that there is a single unit. Right? Or equivalently, it's equivalent to saying that the product is defined everywhere. So really, the feature of having many units in groupoids is in a sense the same feature as only having a partial product instead of a full product defined everywhere. At the other extreme, really, you can just take an arbitrary set and you can easily turn it into a groupoid by just giving it this trivial product. So you just declare that G times itself for any element in your set is just equal to G again, right? And you just leave the product undefined for all other pairs. So whenever G is not equal to H, you just say that GH is not defined. So this is the, I guess, key point where you diverge from groups, right? You can't turn any set into a group, at least not in any kind of canonical way, but you can turn any set into a groupoid in a very canonical but somehow trivial kind of way. But this is important. This will be an important class of groupoids, particularly when you want to see commutative C-star algebras as groupoid C-star algebras. And yeah, again, you kind of have an equivalence here that these kind of trivial groupoids are precisely those where the unit space here, G0, is already the entire groupoid. These are just groupoids of units, right, which are not super interesting. A more interesting example than these last two trivial. It's always good to look at the trivial corner cases, but we also want some interesting examples. So it's a slightly more interesting example you can get from any equivalence relation. Okay, so the equivalence relation, we're viewing relations here as just ordered pairs, right? So they're just pairs of elements from some set X. Okay. And if you have an equivalence relation, then we claim that this product here should define a groupoid. So you say that two pairs can be multiplied if and only if the inner terms here, so the right of the first and the left of the second, if they agree, and in which case you just remove them to get a new pair X and Z, right? Leave it undefined whenever these two things disagree. So why is this true? Why does it have to be an equivalence relation? Why can't you do this with an arbitrary relation? Well, firstly, you need the relation to be reflexive. You want all these identical pairs to be in there. Otherwise, you wouldn't have the required units, okay? Because you wouldn't have range units and source units. So you can easily check that with this product, the range unit is XX, right? You can multiply XX by XY, and the result will be exactly XY. It won't change. And likewise, the source of XY is just the right part doubled. So you need the relation to be reflexive to have the source and range units. You need the relation to be symmetric to have the inverses, right? Again, you can check that with respect to this product, the inverse of XY is really just YX, right? You can always multiply YX by XY, and then you'll get YY, which is a unit. If you multiply on the other side, well, then you get XX, which is again unit. And last but not least, for the product here to actually be well defined, that's why you need the relation to be transitive. Transitivity is saying exactly that. If you have XY in your relation and YZ in your relation, then XZ is also within the relation. Right? I mean, you can always define some operation on G like so. It's just the result may not remain in G if you don't have a transitive relation, and that's not really. Well, then you need to move outside. You need to move to a larger set to really have a groupoid. So equivalence relations are really what you need to define groupoids in this manner. And this already is this is something worth looking at. So let's say we have some finite groupoids. So this yields a C-star algebra in pretty much exactly the same way as we were doing before. Very little change is needed, right? So we look at all the functions from our groupoid G to the complex numbers, and we consider this convolution product. Yeah, because we're dealing with finite things, this sum is finite, and so the sum is indeed well defined. Star operation, exactly as before. A star of G is determined by the value of A at G inverse, just taking the complex conjugate. Whereas sums and scalars are just done pointwise again. I guess the only slight difference now is that to define your two norm, you have to do something a bit different. You now have, in a sense, many two norms because you have many units. So you can always look at this value A star A at some unit X, take the square root. This will always be positive. This will always define a semi-norm. But the key thing is it won't define a norm. Like for some single X here, this could be zero, even if A itself is not zero. A could be supported on some elements which don't have source X, for example. So to sort of counter that problem, what you do is you take the supremum over all the units, and then that will turn your two norm at X into a proper two norm, right? Not just a semi-norm. And then we define the B norm in exactly the same way, looking at the supremum of all these ABs in the two norm over the two norm unit ball. And again, it's basically a little exercise to check that just like before, this still defines you a nice C star norm, satisfies the C star norm equality. Completeness is something you have to think about, but like with finite things, as we're just looking at a finite dimensional vector space here, a finite dimensional algebra, we don't need to check completeness. Automatically, it's complete with respect to any norm. So that's not something we have to worry about. Completeness will become a much more important issue later on, and in particular in next lecture. But today, we're still going kind of easy. So let's look, for example, at a quite instructive example where you look at the full, or I guess you might say total equivalence relation on some set of n elements. So put another way, you're just looking at all pairs where the elements are ranging from 1 to n. Okay, so the complex valued functions on xn here are not, what am I saying? No, this shouldn't be an xn, this should be a g. should be xn times xn. So the c-valued functions on G here, not xn, sorry, these could be viewed as n by n matrices. And a matrix is in essence, right, just a function from n times n to the complex numbers. But so you might write it in a kind of square form, but every entry can be considered as the value of the function at that particular pair, right? And moreover, if you write out what convolution means in this case, well, it looks like this, right? AB at this pair JK, well, you have to sum over all the pairs whose product is JK. But we know what those are, right? The only possible pairs that give you JK are those of the form JL and LK. The inner things have to agree because that's the only time when the groupoid product is defined. And this might, well, this already hopefully is looking kind of familiar, right? This is really just a matrix product, just written out in kind of gory detail, right? So if we're viewing these functions as matrices, then convolution is just the usual matrix product. And likewise, if you look at the star operation, well, the inverse of JK, remember, is just the things reversed. It's just the inverse of JK is A of KJ, right? Taking the complex conjugate. So again, if you're writing this out in matrix form, switching the order here is really just the same as taking the transpose of the matrix and then taking the complex conjugate. This is just the conjugate transpose operation. And these are exactly the operations you do to form the C-star algebra Mn. So in this case, this particular C-star algebra is just the n by n matrices, right? So, and you can generalize this further. You can say, well, I can take any equivalence relation on some finite set X, right? And then you can partition, by definition, you can basically partition this X into equivalence classes of some sizes. I mean, it's not a priori clear what they are, but there will be some finite n1 to nk that denote the size of all the equivalence classes. And just as here we saw that the C-star algebra of G is Mn, here the C-star algebra of G would be Mn plus, Mn J, Mn K, right? Like right up to K. But so what this tells you is that in fact groupoids, just these finite groupoids even, they give you all the finite dimensional C-star algebras. So it does fix this kind of fundamental problem with group C-star algebras that finite groups don't give you all the C-star algebras you would want to necessarily look at, but groupoids do, and they do in a very, very elementary way, right? When you have a finite group, it was not always clear actually how to go from the group to this more kind of standard Wedderburn presentation without doing some kind of heavy calculations. I mean, I think we did one little exercise where we basically used the knowledge of conjugacy classes of S3 or S4, and then some elementary kind of arithmetic to work out exactly what the n's should be in order to get this, right? But that was a very special case. In general, for a general finite group, it might be very difficult to work out exactly what the n's are, right? What the conjugacy classes might actually be. But here it's easy, right? Like, it's very easy to find a groupoid operation by just looking at pairs where you're looking at an equivalence relation with certain size equivalence classes. Yeah, and just, I guess, a bit of terminology here. What this is saying that all finite dimensional C-star algebras have groupoid models. So there's a lot of work on showing that more general infinite dimensional C-star algebras have various Étale Groupoid models. And we'll maybe get to talk about some of them a little bit later. Okay, so that's all about groupoids. No, so this should delete the O there. It should be groupoids. Okay, so now I want to talk about Étale Groupoids. What does this extra Étale mean? So, well, it's all about topology, really. If we want to obtain more general C-star algebras, in particular, even just the commutative C-star algebras, then we really are going to need some topology, right? Because remember, commutative C-star algebras are all those of the form C0x for some locally compact Hausdorff space X, and the topology is key there. Without the topology on X, you can't reconstruct C0x. You can't reconstruct the algebra. So So likewise, if we want to include those and hopefully many more interesting examples as well, then we're really going to need to look at topological groupoids. In fact, what we really want to look at is these Étale groupoids. To find them, just quickly recall what it means for a function to be continuous and for a function to be open. So when you have topological spaces, continuous just means the pre-image of any open set is open. Whereas on the other hand, to be an open map is just saying the forward image, the usual image of any open set is open. So an Étale groupoid is one where all the maps you naturally have here, all the structure maps, the source map, the range map, the product, the inverse, they all have to be continuous and open maps. This open part is key. We'll see towards the end why you really need to have these maps to be open. In particular, you really need to have the source, or equivalently the range, to be not just continuous but also open. Otherwise you won't be able to define convolution, and you won't be able to find the C-star algebra in a reasonable way. Not without working with more complicated things known as Haar systems. But we don't want to talk about those here. Okay, and when we have a groupoid with such a topology, with an Étale topology, we naturally just call it an Étale groupoid. And maybe just a few comments on the definition here. So you can see there's already a bit of redundancy, because if you look at, say, the inverse, well, we know that that's an involution, right? The inverse is itself. And what that tells you is that forward images of the inverse map are exactly the same as inverse images, right? As pre-images. So what that tells you is that the inverse function, is an open map if and only if it's a continuous map. So you only need to assume one or the other. Also, if you look at, let's say, the source, well, that's both open and continuous if and only if, well, if it's open and continuous if all the other maps are already open and continuous, right? Simply because source of G is exactly the same as the range of G inverse, right? So if the inverse map is continuous and the range is continuous, well, this tells you the source map is also continuous. And likewise, if the inverse map is open, which is the same as continuous, as we just said, and we know the range map is an open map, well, then the source map has to be an open map as well. And maybe just something to point out is that when I say the range is an open map, I mean it's an open map to G itself, taking G, the whole of G, as the codomain. And so in particular, if you look at the image of the entirety of G, which is the entire unit space, well, that has to be open within the larger space G. So when you're talking about open maps, the codomain is important in some sense, right? Like if I just said it was open as a map to G0, well, then you wouldn't know anything about how G0 sits within G. But what I'm saying is that the unit space here has to be open. And maybe a more familiar concept you might know about is what a topological groupoid would be. So a topological groupoid would be defined like a topological group, right? And that is to say that the structure maps are just continuous, where you don't require them to be open. And in fact, here you can see immediately it's really enough for the product and the inverse to be continuous, because both the source and the range maps here, well, they're just combinations of inverses and products, right? So they are automatically continuous in that case. And like I said, this is not enough to do what we want to do, but it's worth mentioning, because if you already know you have a topological groupoid, you don't have to check all the other conditions I mentioned to be Étale. It really just suffices to check, for example, that the range map is an open map. Right? So if all those relevant operations are continuous, including the range, all we have to do is check the range as an open map as well, in order to determine that the other maps are open, and so that we have an Étale groupoid. Often something like this is usually used as the definition of Étale. But I thought it's more natural maybe at first to say Étale just means all the maps have to be continuous and open. So to see why this is true, note that really all we have left to prove is that the product map, this multiplication M here, is open whenever it's defined, right? It's open on G2, considered as a subspace of G times G in the product topology, right? Because why? We know that R is open and continuous. Therefore, the source is also open and continuous. We said that. We know that the inverse is continuous, which is, as we said, equivalent to the inverse being open. So that's fine. We know the multiplication map is continuous. The only thing that left is to show that this is open as well. So why would that be the case? Well, let's first make a little bit of an observation. Let's look at this projection map P. So look at the projection onto the first coordinate as a map on the composable pairs G2, right? So, well, if you look at that, we claim that this map here, P, is actually an open map. To see that, well, just take any basic open set. So any basic open set in here is determined, it's the subspace topology. So it's determined by these open sets O and N. So any basic open set on G2 has to be just the intersection of G2 with all pairs, lying in O times N. Okay, but think about what that means here. Well, the projection of the first quadrant of that's really just all those elements in O, right? Such that G and H, for some H within N, actually lies also within G2, right? But to be lying within G2, well, what does that mean? It means that the source of G has to be equal to the range of something in N. As soon as that happens, it's in G2. So the source of G has to lie in the forward image of this range map R here, right? But put another way, this is really just saying we're looking at the intersection of O with all those elements in the pre-image of S restricted to O. Right? So we know that S is not, I should say, open. So there is perhaps a little bit of an issue here because you're looking at open set here. This really should be an open slice. You should really restrict this O first actually to an open set on which S is injected. Otherwise, you can't properly define. Oh no, I think that's, let me see. Really. No, I think it's fine, right? So I'm not looking at this S restricted to O as an injective function. This is just a pre-image, this S to the minus one here. Okay, I think it's all good. So, okay, look at the restriction of S to O, but then look at the pre-image of these units you get from the forward image of N. Okay, so the pre-image of that lying within O, okay, that gives you exactly this set here, which is exactly the projection onto the first coordinate. Okay, and now that, you'll see, is open, right, by assumption. So by assumption, R is open. So by assumption, the forward image of N, which is an open set, is again an open set. But by assumption, S is continuous, right? In particular, S restricted to some open set is still continuous, right? So if you look at in fact, I don't know why I got this restriction here, because the restriction here, I guess, is, that's exactly the same as saying O intersection that, right? But in any case, the inverse image of S of this guy, it's open, has to be open, right? And if you take the intersection with an open set, again, open. So everything is open here. Okay, so that shows you that P is an open map. Now, to see that the product, the multiplication, is again open, we do something kind of similar. So again, take two open sets O and N. Note that GH inverses in O is exactly the same thing as saying G is within OH, right? For those valid products of O and H. So put another way, if you look at all products from O and N, what that's saying is that it's really all those elements of G, such that there exists some element of N, such that GH inverse is within O. And now this is looking like something we can handle, because this, well, to say that there exists some element H and N such that GH inverse is in O, what's that really saying? Well, you're looking at the inverse image of the multiplication map, the inverse image of O, right? You want the product here to be within O. But not only that, you only want to consider those products where H here, or H lies in N, or put another way, H inverse lies within N inverse, right? This set here. So we know that M is continuous, so this pre-image here is continuous. We know that N is open, so its inverse is also open because the inverse map is continuous. Therefore, a product of two open sets is open in the product topology. We can take the intersection with this set we also know is open. Again, we still have an open set. So this whole thing in the square brackets here is open. And we already showed above that P is an open map. So the forward image of this open set under P is again an open map. So that finally gets us what we want. So this product here, where you're looking at all the valid products, right? You won't always be able to define, you won't always be able to multiply any element of O with any element of N, but all those ones which are valid products. This shows that this is indeed an open set. So M is indeed an open map on all those composable pairs. Okay, so that's one little proof. Now to go further, I want to talk about slices. So I guess I could have really talked about this earlier when I was talking about just groupoids in the algebraic sense. So a slice, and sometimes called a bisection, is just some element on which both the source and range maps are injected one-to-one. Okay, a nice little characterization which will be useful is that B is a slice precisely when, if you look at these products here, BB consisting of something from B inverse, and the same reverse, that all of those are always going to lie within the unit space. Oh, pardon me. So it's a fairly simple proof. So let's say B is a slice. Take some element in my slice B. Well, we know that the source of B inverse is exactly the same as the range of B, right? So the only valid products here in this big B, little b inverse, there's only one, like, so it's a slice. So there's only one possibility, right? Like the range, if I was to have any valid product here, then I would have to pick some element in big B, whose source unit is the same as the range unit of B inverse. Okay, so yeah, so I think it should really be reversed, right? So I really should be saying the range unit of B inverse is the source of B to be able to make, for it to be relevant to this state. Okay, but what I said still holds true, right? You need, for any product here to be defined, you have to have the range, the source, the source of this element in big B to be from the range of little b inverse. We know B does the job, and we know the range is injected. So that means that's the only possibility. Okay, so that is equal to that. And likewise, which I guess is really where this would come in, you know that B inverse B is, there's only one possibility for what the valid products could be here. So again, it's B inverse B, which lies in the unit space. But this is true for all little b's in the big B's, right? So this tells you that in fact, these guys here, which is basically the union of all of these sets of this form, right? They again have to lie within the unit space. So slices indeed satisfy this inclusion right here. Conversely, what if we have this inclusion here? Well, what does that mean? Well, let's take two elements then, which let's say share a source. So let's take A and B, which have a source, which have the same source, and which is therefore the range of B inverse. Okay, well, if that's true, that means we can multiply A with B inverse, and we get a unit. Okay, but if it's a unit, well, okay, then I can say A here is equal to A B inverse B, right? This is just a unit, it shouldn't affect A. I know it's a valid product because A B inverse is a valid product and B inverse B is a valid product. Okay, but at the same time, I know that A B inverse is a unit, so I can also just delete this and I end up with B. So in fact, these two things sharing a source had to be exactly the same. And likewise, if they share a range unit, then they have to be identical. So B is indeed a slice as long as this condition here is satisfied. Okay. And this gives us maybe a simple way of showing that slices are actually closed under taking products. So let's look at a product of two slices B and C. Well, then you can rewrite it like this. Then C inverse, this consists of units. So really, that's going to be just included in B inverse, which itself is included in the unit space. And likewise, the other way around, right? So this does indeed say that BC is a slice, that slices are closed under taking products. So keep that in mind. And now we want to talk about open slices. So these play a pretty important role in the theory of Étale groupoids, and particularly functions upon Étale groupoids. So a nice, I think, equivalent definition or equivalent characterization of Étale groupoids involves these open slices. And I'll prove one direction first. So let's say we have an Étale groupoid G. Now it turns out that this will then automatically have a nice basis, a basis of the topology, consisting entirely of open slices. In fact, you can take all the open slices as your basis. Right. So CY, well, recall that the unit space itself of any Étale groupoid has to be an open set, simply because the source or the range is an open mapping. Okay, we know that product is continuous. We know that if I take the product of these two particular elements, G and G inverse, that's definitely a unit. Well, the continuity tells you then I can get two open sets, one containing G, one containing N, such that their products still lie within this open set G0. Right? So O N inverse in this case. So yeah, you can say that N covers G, or equivalently N inverse contains G inverse, right? So I found this O and N satisfying this, and then I can, do exactly the same thing, on the other side, right? So I can look at G inverse G, and again find open sets L and M containing G such that L inverse M now is contained within the unit space. And now just to get what I want, I just take the intersection of all of these open sets, L, M, N, and O. It's still an open set, definitely. They all contain G, so the intersection still contains G, right? And by shrinking these sets, because these are contained within O and this P is contained within N, well, then certainly the same thing applies, right? The P inverse is still contained within the unit space. It's possibly smaller. And likewise here, right? So this tells us now, once we take the intersection, we get this P, which satisfies exactly what we want to tell us that P is indeed a slice, an open slice. Okay, and to see why it's a basis now, just take any arbitrary open slice containing G. So to be a basis, you have to show I can find some even smaller open set, right, which contains G, which lies in my basis. And it's easy because I've got my P here, it contains G, well, then I can just take the intersection. It's still open, and it's still a slice because any subset of a slice is a slice, right? If the source and range are injective on some sets, well, then they're definitely injective on a smaller set. Right? So this gives us exactly the open slice we need to show that the open slices indeed form a basis for the topology. Okay, so what this essentially tells you is that these source and range maps, so they're not only continuous and open maps, which is true by definition of Étale, but they also have to be locally injective. So they definitely won't be injective in general, but what this says is that around any point I have an open slice, and by definition a slice is something on which these two are injective. So indeed it's locally injective, and being continuous, open, locally injective, by definition that's saying you have a local homeomorphism. And often that's actually used as the definition of an Étale groupoid. Like an Étale groupoid is a topological groupoid such that the source, or equivalently the range map, is a local homeomorphism. But yeah, but I think personally I find it's clearer to me if I look at it in terms of open maps. This is really the key. The fact it's a local homeomorphism, this local injectivity here, that's, to my mind, better left as an observation after the fact. I mean, it's an important observation certainly, but when you start out, I think it's really better to deal with open maps. So yeah, this is, in summary, exactly what I was saying. Topological groupoid is Étale precisely when the source of range is local homeomorphism. Okay, let's continue to talk about open slices. Let's prove the reverse direction of the result I just gave you. So what I want to show is that a groupoid is Étale, in fact, if it has a basis of open slices. But it has to be a bit more than that. You have to have a basis of open slices, which is still closed under products, right? And is also closed under taking inverses pointwise. And if it was just an arbitrary basis of open slices, that would not be good enough. It has to, I mean, if you know about these things, it has to form an inverse semigroup with respect to these canonical pointwise products and pointwise inverses. But we don't worry about that terminology if you're not familiar with it. Okay, so assume we have one of these nice bases B. So you might call it an Étale basis or something like that. So we have a basis. Well, you immediately can tell from this this first part that O inverse has to be in B whenever O is in B, that the inverse is therefore a continuous or equivalently an open map, right? Like to show this, of course, it suffices to work with a basis, not with arbitrary open sets. Then follows automatically for arbitrary open sets. Okay, but how about the product? Let's say, why is the product continuous? Well, let's take two elements for which the product is actually defined, and let's look at some open set containing the product. So we want to show continuity, right? We have to find some open subset containing G and open subset containing H, such that those products still lie within O. So firstly, well, we can definitely take some open N, right, containing H, and well, if GH is within O, then G is within OH inverse, true, right? And if H contains N, well, that's definitely within ON inverse. Okay. Also, we know that, yeah, did I say open? This open N here, this should be a slice, right? Otherwise, what I'm going to say next, I think, is not going to work, right? So it has a basis of open slices by assumption, right? So in particular, I can find N, which is not just open, but an open slice containing H, right? Okay, and once I've got that, then I know that O and inverse is open, right? By assumption, I can take inverses, I can take products. I'm still within my basis. And if I look at this product here now, the fact that N is a slice means that these products all have to lie within the unit space. And these don't affect O here. So that's really just O itself. But this is what we want, right? We wanted some open set, in this case, O n inverse containing G. And we wanted some open set N, in this case, open set containing H, in this case, N, such that the products of all those still lie within the given open set O. This is exactly what we wanted. Okay, so that tells you the product is continuous. And remember, one of our results is that the only thing extra you have to check to verify Étaleness is that the source is an open map. And why is this true? Well, just take any, take any open set, take any element within the open set. Well, I can always find some smaller open set, some smaller open slice, in fact, which still contains G, by assumption that I have this basis of open slices. And then what happens? Well, you look at the source of G, it's this, right? Which is certainly lying within N inverse N, right? And that is open, lies within our basis here. And that, because N is a slice, we know that is exactly the image of the source map, right? If this were not a slice, well, then maybe this would have elements outside the source map. But because it's a slice, we know this is exactly the source map of N. So what we found is some open set, Sn, which contains the source of some arbitrary element G in N, and which still lies within the image of the source of O. As G was arbitrary, this tells you that you can write SO as a union of these smaller open sets that form Sn. So that means this itself has to be open as well. S is therefore an open map. And maybe cute little exercises is to show that actually it already suffices to be a sub-basis. So remember, the sub-basis of a topology is one where the finite intersections form a basis. And a basis is one where the arbitrary unions form all the open sets. Right? So the basic idea is that even if you start with a sub-basis and you know it's closed under products and inverses, then when you take finite intersections, you can again show that it's closed under these products and inverses. And then this result will tell you that again, you have an Étale Groupoid. Okay, so how are we doing here? Okay, so it's probably about time to give you some nice examples. We've done the theory pretty thoroughly. So, well, again, we can go to for some trivial but important examples nonetheless. Take any group, just give it a discrete topology. Well, then that's definitely going to be an Étale groupoid. I mean, because it's discrete, all maps are going to be open and continuous. So that's one way of seeing that it's Étale. For another easy way of showing it's Étale is to note that that slices of a group are just singleton sets, or the empty set, I guess. But if you have a basis of open slices, that means you would have a basis of open sets. You have a basis of singletons, right? And the only topology with a basis of singletons is the discrete topology. Okay, so if you have a group, then Étale is equivalent to discrete. Étale is an extremely strong condition on the topology you put in place on a group. Right? If you only had the topological group, well, there's plenty of those which are not discrete, right? And then you get Haar measures, and you can use those to define convolution in a different way. But for us, we're looking at Étale things, so that automatically implies all groups are discrete. The other extreme is when you have a topological space. Well, this always forms an Étale groupoid under this trivial product we mentioned before, where the only products are of the form XX, right? XX is equal to X. And indeed, in this case, you have, well, everything is a unit, right? And so the product of any two open sets O and N, that's really just the intersection of O and N. And the inverse map in this case is also trivial because, well, the inverse of a unit is getting a unit. So that's like, yeah, trivial but important because we will want to see groupoid C-star algebras include C-star algebras coming from topological spaces. Again, moving into something slightly more interesting, we can look at equivalence relations on some topological space. So these equivalence relations, they will always form a topological groupoid in this relative topology with the same operation as before. Remember that you say you take a product xy times yz, and you define the product of that to be xz, right? So they will always, it's not too hard to check, form a topological groupoid. The source, the range, the inverse, the product will be continuous maps. However, very often, maybe in fact almost all the time, they will not be Étale, right? Not in the product topology. For a simple example, you can just take the full equivalence relation on some set X, right? Or some topological space X. As long as this topology is not trivial, as long as it's not discrete, then you know this cannot be an Étale groupoid, right? Because if it was an Étale groupoid, then the unit space in particular would be open. But the only way some basic set in the product topology, right, something of the form O times N for open O and N, the only way that could lie entirely within the unit space is when both O and N contain a single set, right? The same single element, I should say. If they contain two different elements, well, that would be in the product, and this would lie outside the unit space. So this looks to be a pretty serious issue, especially if you want to use equivalence relations to define Étale groupoids. Turns out it's not quite as fatal as you might think, because often there's a nicer or finer topology around, which is still kind of natural in some sense, and which does end up giving you an Étale groupoid. And I can give you a nice little example of this right now. So I'll call it the car groupoid. I'm not sure if that's the best name, but it corresponds to the car algebra. So this is the one I will use. So to define the car groupoid, let's look at all functions from N just into some two-element sets. Let's call the elements 0 and 1, just to make things easy. Which you can, of course, view as infinite strings of zeros and ones, right? That's what a function from the natural numbers is. Now, given some finite string, so some function from some finite n, or some set with n elements, 2, 0, 1, there's a very easy way of defining, and some infinite string. There's an easy way of creating a new infinite string just by tacking the finite string onto the left of the infinite string. So you just concatenate these two things to produce a new infinite string. And that's useful because that gives us an easy way of defining what's known as tail equivalence. So the Taylor equivalence relation on this set X of infinite strings of zeros and one is basically saying two elements are equivalent if they're equal beyond some point. Right? As long as there is some n such that sure the two sequences can differ up to that point n, but from that point they're all exactly the same. Right? That gives us a nice equivalence relation. I mean, verifying all the properties, it's pretty obvious. I guess it's reflexive because you can take S equal to T. It's also pretty immediate. It's symmetric because you can switch S and T here, no problem. And it's transitive because if, well, this is true for some n, and then you have this being equal to something else beyond some possibly larger m, well, then you can just take, you know, that new m as the point beyond which these the leftmost and rightmost sequence agree. Okay, so I mean, it's fairly clear. Just write it down if that argument didn't convince you. But this gives you an equivalence relation. Okay, and note by definition almost this G here consisting of all those pairs. Well, it's the union of all these what you might call cylinder sets, G, S, T, where the S and T here is ranging over all those finite sequences, those finite strings of zeros and ones. And these cylinder sets are useful because they give us a nice topology, right? If G is the union of these sets, well, then I can always look at the topology they generate, right? Taking this as a sub-basis for the topology. But in fact, it's better than a sub-basis. It really is a basis. So the way to see this is to note that if you have two cylinder sets, well, either one is contained in the other, you know, namely if one cylinder set is basically determined by extensions of another, right? Where you have some finite string R and Q such that this is you're just tacking R on the end of T and Q on the end of S. Or alternatively, the cylinder sets can be disjoint. Yeah. If V is not an extension of T and T is not an extension of V, or if S is not an extension of U, or if U is not an extension of S, then there's no way that these two cylinder sets can contain anything in their intersection. Right. So in particular, the cylinder sets are closed under finite intersections. This says something quite a bit stronger, but in particular, they're closed under finite intersections. So they don't just form a sub-basis, they form a very nice basis closed under finite intersections. To show that this really does define an Étale topology, it's convenient, I think, to use this characterization I had before about having a basis, which we already have, which is closed under products and inverses. So note that if you take a product of two cylinder sets here, where the string S here is just a shortening, or the string SQ here is rather an extension of this string S here. Well, then when you think about it for a second, you'll see that, well, okay, if I have two strings, you know, one starting with T, one starting with S, and I have another two strings over here, one starting with SQ and another starting with U, well, then looking at the left and rightmost, right, they also have to agree beyond Q, basically, right? So in other words, this U, if you're looking at all the sets which on the right start with U, on the left start with T, followed by Q. So this Q kind of gets mapped over to here. But in any case, it gives you another cylinder set. And likewise, if this bottom guy here is really just an extension of this top guy on the right, well, then again, you'll get yourself another exactly the same cylinder set, right? Okay, so what it's saying, it's these cylinder sets are closed under products, and it's pretty immediate that they're also closed under inverses, because when you're looking at an equivalence relation, you know, the inverse just basically swaps the two coordinates. So in particular, gives you the same. What am I doing? This should be TS, right? It does swap the order, right? GTS inverse should be G, T on the bottom now, S on the top. So sorry for that typo. Okay, in particular, if you look at, you know, the product of some cylinder set and its inverse, well, then you're just going to end up with GTT, which is basically all those identical pairs which also start with T. In particular, the pairs will always be identical in this cylinder set here. Okay, so therefore, this lies completely in the unit space. Remember, with equivalence relation, this is exactly the unit space. Okay, so what this tells you is that, well, not only are these cylinder sets closed under products, under inverses, but also they satisfy this key condition here and the reverse, which tells you it's actually a slice. So I have a basis of open slices, closed under products and inverses. Therefore, by that equivalent notion, that result I had a bit earlier, G has to be an Étale Groupoid. Okay, and this is so yeah, this is a nice, I think, non-trivial example of an Étale Groupoid. It's not a group, it's not a space, it's some interesting thing in between. And indeed, it defines a quite important C-star algebra, as we will get to eventually. But maybe just before moving on, though, let me point out that this the original topology you would expect to put on these infinite strings here, right? That would just be the product topology, right? And so what that does mean is that you can identify X with the unit space, and that this identification, in fact, really gives you the product topology you would expect. That these sets of the form GSS, which form a basis for the unit space, right? They're really just coming from all those strings X, which contain some fixed finite string S, right? And think about it for a second, that's really just the canonical basis of the product topology of infinite strings of zeros and ones. Okay, so it's a nice homeomorphism. The unit space is indeed topologized as you would expect. However, the whole groupoid, the more general pairs, these are not topologized in the product topology sense, right? If you think about what the product topology on these arbitrary pairs now, well, I guess not arbitrary, but the pairs that actually lie within your equivalence relation, well, the basis in this case would consist of these slightly different cylinder sets, G underline TS, like so. So it's kind of like the sets before, where they have to start with T and they have to start with S. But the key difference is you're also allowed to take any arbitrary P and Q and tack that onto the end of T and S before you deal with two strings that are the same. I mean, the X's have to be the same beyond some point, because we want to deal with pairs that are actually lying within the equivalence relation. But even though they're the same beyond some point, that point can be quite a bit after T and S. There's no restriction here on the size, the M here, there's no restriction on the size of these Q's and P's. And so that is really what is the kicker that tells you that you're not going to get that this is a really fundamentally different basis, if you like. But one thing is clear, at least, that the sets of this form are indeed unions of sets of this form, infinite unions, right? Okay, so in particular, any open set in the product topology will be open in this Étale topology we've just defined. But the converse is definitely not true, right? This product topology is strictly coarser. And you could look at various sets, I guess, but in particular, just look at the unit space, right? The unit space is open in the Étale topology. It has to be. However, this does not contain any of these slightly more, these bigger cylinder sets that form GSS. Simply because for any fixed S, right, I can always extend in two different ways up to some point before I again make the sequences the same. And that means that if I extend them in different ways, they're immediately going to lie outside of this unit space here. Okay, so this is one of those examples I mentioned where you don't want to look at the product topology. However, there's a very natural finite topology which does make your groupoid Étale. And a finite topology which doesn't affect the units. The units will still have the sort of right product topology. It's the more general ones that don't. And let me see, how am I going for time here? Okay, so yeah, I guess I can quickly run through this. So we want the whole point, right, of defining these Étale groupoids, we've looked at the definition, we've played around with the definition of love, we've looked at some examples. The whole point was we wanted to be able to look at some kind of convolution algebra to get interesting C-star algebras out of this. And you can do this in pretty much the same way, at least up to a point, as we've been doing before. So let's look at continuous functions now. Say we have two A and B, which are continuous with respect to some Étale topology on G. So we'd like to be able to define this convolution like before, where you just take the sum, right? The value at F is the sum of all these products here, where F has to be equal to GH. But you can immediately see two kind of big problems here. And the first is a very big problem, and that is the sum may not even really be defined, right? It may not be finite. You're dealing with these groupoids, which could be infinite. Well, of course, there could be infinitely many G's and H's such that this product is non-zero. I mean, if they converge in some sense, right? If this was a countable sum, and as you take the larger and larger finite sums, for example, and these approach zero fast enough at least, then that would be fine. You could still define it in a perfectly good way, but sometimes even that fails if you're just looking at arbitrary continuous functions on G. So that's a problem. And another problem is that even if the sum did happen to converge, it's still not clear, at least, that the resulting product you get will again be a continuous function, right? We want to turn this guy into a C-star algebra. So the product of two things should again lie within the algebra we're trying to define. So to resolve both of these issues, we need to be more restrictive about the kinds of functions we're dealing with. Can't deal with arbitrary continuous functions. To be more precise about how we're going to restrict these, let's define the support of, at the moment, an arbitrary function from G to complex numbers. So the support is, as you expect, just all those elements in G which are not mapped to zero by our function A. So instead of looking at C of G, I'm going to look at what I call S of G, which is exactly all those continuous functions from G to complex numbers, such that the support is a slice of G. Right? So this is much more restrictive. So this is our first attempt to at least show that this product here is going to be well defined. And indeed, this is what we will prove. So if you have two functions and at least one of them, if they're both continuous, and at least one of them is supported on a slice, then you do have a well-defined product. And not only that, but the resulting product is again going to be a continuous function. To see why, well, notice that, okay, well, we sort of restrict to two cases. We want to show that AB is, well, let's say AB is first defined and continuous on all those elements here, whose range also lies in the image of the range of the support. So in that case, you'll see that, well, okay, I have a function here and I'm looking at all those G's and H's such that this product is non-zero. But if A is supported on a slice, well, there's only one possibility for G, right? We know the range of F here has to be the same as the range of GH, which is just the range of G. But the range map has to be injective on the support of A, because A is supported on a slice. So if I already have my range of F, if I already have my F fixed, and I look at the range of that, then there is at most one G here whose range could possibly make this product here non-zero. Okay. So that tells you it's well defined. And indeed, to see it's continuous, well, let's look at this function. What is that unique? Well, I've written, let's see here. So what is this unique G here? Well, it's actually going to be T of F, let's say. Let's define a function T of F. So T of F here is basically the unique element of the support of A, right? Such that the range of that element is the same as the range of F. Or put another way, it's what you get from mapping F by the range map and then taking the inverse map when you restrict the range to the support. Because the support is a bisection, this inverse map is indeed a continuous function, right? Okay, and so well, range map is an open map, and this range restricted to support is again a continuous map. So the inverse is again going to be an open map, right? So this T here is going to be, well, this T here is going to be a continuous map. The composition of continuous functions gives you a continuous map. So I guess it was the other way around. Range is open, then continuous. But yeah, anyway, T is definitely continuous, right? And so we know that this is the only element we care about in this sum. It's T of F. And the only other possibility then for H is to look at F TF inverse. And now we can see that everything is continuous, right? T of F is continuous, mapping by A, it's continuous because we're assuming it's A is continuous function. TF is continuous, the inverse of that is again a continuous map. The products are continuous, so taking the product with F is continuous. The value of B at that thing is continuous because B is supposed to be a continuous map. So everything now is continuous, right? And so this all works out. And this, I guess I should point out, is sort of the key point where you're using the fact that the range map is not just continuous but open, right? So here, okay, you're using continuity, but here to declare that, or to derive that T is continuous, you're looking at this R inverse function. So for that to be continuous is the same as saying that R is really an open map, right? Okay, so that's, yeah, if it wasn't, yeah. This continuous, the inverse, yes. So this is really where you're using the étaleness. Being a topological groupoid would not suffice at this point. Okay, AB is continuous on this, which is what I just said. It's continuous. Now you just have to worry about the other elements, but that's actually kind of easy in some sense, because all the elements outside of this, really, these sums here will be zero everywhere. For continuity, you have to be a little bit more careful and say, well, for every epsilon greater than 0, I can find some open set containing this set here, this closed set here. So you can find some open set on which A and its AB has a modulus at most epsilon. Right, and then and once you know that, well, that tells you that AB is also continuous on the complement, where it all takes the value 0. Yeah, so that's sort of the first step to defining, the algebra we need. But I can see I'm running out of time, so okay, let me go through one more slide. So that works for the yeah, do I have time? Let me just check, do I have time? Yeah, so I'm not sure I really have time to deal with this, but this is, like I said, this is the first step you need to be able to define convolution, to be able to define an algebra, and then eventually you'll want to also do some completing to actually get a C-star algebra as well with respect to appropriate norm. Here you'll have different norms to choose, and this is something we'll talk about more next week. But I think this is probably enough for today. So thank you for your attention. Does anyone have any questions? Doesn't look like it. Okay, well then I guess that concludes today's lecture, and hopefully see you all again next week.